You can set that after programming, and it will like disable JTAG. And you can do this in waiver testing or in product manufacturing or where you want. And an optional extension of this is a secret unlock sequence you can run through to re-enable JTAG if you really need to do debugging in field. The problem is that asymmetric operations like RSA are usually not feasible to implement into hardware, so they're usually doing symmetric challenges, and they are really hard to make secure against replay attacks because you need a good random generator and you need some good encryption and all of that. So be careful with chips that implement JTAG Unlock by doing some secret things, even if there's a hard secret like a key embedded into the device. The question is again always, how are those security bits being programmed? And the answer is usually over the debug bus. So the conclusion is that the debug bus is when the device just exits the factory, it's still in a debug mode, so every debug functionality is still accessible, and it will be locked down more and more when it leaves the factory. So the initial production state is usually the most insecure device state, which is, sounds pretty good. It would be bad if it would be the other way around. But the question is, how one-time programmable is one-time programmable really? So, for example, flash-based OTP, you can mess around that with strong UV light, like you erase an EEPROM. You can apply the same technique to a chip. Or eFuse-based OTP, where you physically blow a fuse on the silicon, sounds pretty secure, but actually it's not that you blow a fuse and it makes pop and there's a small hole in your silicon. In fact, all you're doing is like changing the resistance of some element on your chip and hoping that the resistance is high enough that this is actually sensed as a blown fuse versus a non-blown fuse. So for eFuses, sensing eFuses in the correct way is rocket science, and it's very important to have the proper reference supply. So what vendors usually implement is a low voltage lockout, so it won't boot up at all if the voltage isn't enough to reliably read eFuses, but not all of them do. Another interesting thing is some chips have a very strict power sequence requirement, like if you have like a core voltage and an I/O voltage and another core voltage and something. It's very important, and the datasheet says you need to apply them in the right order. And if you don't do this, bad things will happen. But what usually nobody can tell you exactly is what will happen if you do that. And even most hardware designers can't tell you really. They can tell you it's out of specs, but it's hard to tell what actually happens. And you should definitely try what happens, especially to sensing fuses. And I have seen some part failing at sensing fuses if you apply voltages in the wrong order. It would sense all fuses as being 0. And this is the default state after production, so it's the most insecure state. So if you want to re-enable JTAG on a device where the JTAG, it is not really a fuse there, but some flash thing. If you would want to re-enable JTAG, you would have to set up a wrong power sequencing, and it will come up all in insecure mode, and you could use JTAG again. So this is definitely something you need to be aware of, that having an eFuse doesn't mean that the eFuse actually works in every combination, and that the hacker isn't able to make the environment bad enough that the eFuse might fail. So, yeah. So that's actually most of it. I hope you got a good understanding on what you can do with JTAG. JTAG should be considered as a tool for people, so you should be aware what you can actually do with that tool. So if you have built some hardware with some chips on it and you don't have much documentation about it, try to see what you can do over JTAG. Try to find the hidden test modes. And by doing the algorithms I've presented here, I think you are able to like map the JTAG space and see if there are hidden test modes in it. You might not find all, but there are usually a lot of them. And be sure that the manufacturer of your chips tell you all about the security implementation of these test modes. Vendors are usually quite shy about telling things, because if you have a chip that can be locked down, the vendor still usually wants to have a way to find out what failed if a lockdown chip failed. So they sometimes have test mode which can unlock a chip or run some test pattern even on a locked chip. And you should definitely be aware of that those test modes exist, and get the right input from your vendor, and be sure that the vendor is not hiding stuff from you, because it affects the security of your hardware and your secrets. Okay.
If there are any questions, please come to the microphones and the else. Yeah, go ahead.
My question is, do you know about some people who use power glitching in order to disable the JTAG disabling in the beginning of the boot process?
Sorry, can you speak a bit louder, please?
Yeah,
I'm sorry.
Do you know if some people use power glitching in order to skip the instructions that disable the JTAG disabling function in the beginning of the boot process?
Yeah, so using voltage glitching to skip that instruction is definitely a possibility. So this is another way why you should not rely on your code disabling JTAG.
Exactly, yeah.
So, and yes, I think that's also how some people have been successfully able to read out those LPC microcontrollers.
Okay, thank you.
Okay, I don't see any more questions, so thank you very much.